we're going to begin the study of the second lesson in the Classical Liberal Arts Academy's Modern Biology course. In our first lesson, we studied an introductory chapter that introduced us to the study of biology and gave us a definition of biology. We talked about some general principles that relate to the study of the natural sciences, and I warned students that we're often going to find that science doesn't stick to its own definitions and rules. And I showed you a few examples of that from the first chapter itself. We're going to continue our study here in chapter 2 and move into the beginning of the study of botany. And in this chapter, what we're going to do is lay down a few general principles and learn a few general lessons about the basic elements of the natural world. Now remember, science claims, scientific thinking claims to be thinking that is based entirely on conclusions drawn from the observation of material things around us. Again, science claims to be knowledge drawn from conclusions that are themselves drawn from observations of material things in nature or around us in the natural world. Everything we read, I want to challenge you to think about critically and ask yourself, is this being proven to me scientifically? Is this being proven by the observation of the material things around me? Or am I being asked to grant or to assume things that maybe others claim to have observed, or other conclusions that others have drawn based on observations they claim to have made? And if it's so, if it's not based on direct observation of material things, how certain can I be that any of this is true? And what happens if we start to build what we're calling scientific knowledge on points that are themselves not demonstrated to be absolutely certain? We're just building on sand. And so we want to make sure that we're conscious of what's being said in our lesson that's actually based on demonstrative proof and is certain, and what is merely being offered to us to be taken for granted and assumed. And we have to ask ourselves, if this is in fact scientific, why ought it to be assumed? Isn't that defeating the whole point of scientific learning? So let's go through this chapter. I'm not being negative, excessively negative, because as I said, scientific research and observation is very valuable if it's true. But what's not valuable is using science as a disguise to simply teach a different philosophy or religion and ask us to believe things just as we're asked to believe religious teachings. I believe that God created heaven and earth. I'm told that in sacred scripture, and I believe it as an article of faith. Scientific knowledge should not require that I believe it or trust someone. It's supposed to be knowledge that's based on the observation of the material things in the natural world. So let's make sure that we keep science accountable. Because if we grant things that are not true, if we assume things that are not proven true, we may in fact be assuming and granting things that are false and building a system of knowledge, a science that's actually false. So let's be careful as we study the natural sciences and here in biology. So let's read together the second lesson in biology. In the introductory chapter, we learned that science concerns itself with matter and that the science of biology is concerned with the study of this matter when it is in a living state. In order to understand this definition, we must first get a conception of what matter really is. So we're going to supposedly clarify what matter is. If you take a piece of ice in your hand, you are aware that the ice is cold and that it has weight and a certain form or shape. We call it a solid. A few minutes exposure to the warmth of your hand will change this solid into a liquid. If the water thus formed is heated over a flame until it boils, it may be changed again, this time into a gas, which passes off into the air and becomes invisible. The ice has successively changed from a solid ice cube to a liquid, the water, then to a gas, the steam absorbed into the air. In each state we could measure it and weigh it. In each form, it occupies space. It must be considered matter, whether in the form of a solid, liquid, or gas. All right, so now what we have to be careful with here is we're being told that something that is invisible, remember we're told that the gas passes off into the air and becomes invisible. We're being told that that's still matter. So matter isn't so simple. It's not so simple as something that can be observed with the senses. Okay? Something that we're conscious of, but it may not be perceived. So for example, in the air around me, I can call it air based on my senses, and that's what the classical philosophers did. They identified the element as simply air. And we can all agree that I am surrounded by air, and that air is sensible, that air is perceptible. But modern scientists, as we'll learn, will tell me more about the air, that it contains certain different chemicals, that it's made up of different gases, and so on. And these things are not, to the senses, observable. So we have to be careful, all right? Matter may be, according to this definition, may be imperceptible, may be invisible, may be impossible to see, feel, taste, touch, smell, and so on. And that's a strange idea. Matter may be imperceptible to the senses. Okay, let's keep that in mind. The sciences which treat chiefly of the properties and forces of inorganic or dead matter, as we learned in Chapter 1, and of the relations of the parts of the substances composing it, are known as the sciences of physics and chemistry. So we learn that biology is the study of living matter. Physics and chemistry, generally speaking, are the studies of inorganic matter. And as we continue in the natural sciences through your education, we're going to go into physics and chemistry as well. We're starting with biology. All the building materials of this universe, here's where we have to be careful. All, notice the phrase all the building materials of this universe, both living and lifeless, are classified by chemists as either chemical elements or chemical compounds. So let's pause here and let's realize that chemists, people who study chemistry, they classify all the building materials of this universe as chemical elements or chemical compounds. What science cannot say is that this is real or true. We're simply being told that chemists call or classify all the building materials of the universe. Notice how this goes. All, right? A universal statement that's supposedly based on scientific experimentation of observable matter. The chemists are making the claim that all the building materials of the universe, not of the earth or of what they have observed. The claim is that all the building materials of the universe are such and such. And this is an example of a statement that is not scientific. It's impossible that any chemist can make a universal statement about all of the building materials of the universe. We're not talking about Earth or even the atmosphere around the Earth. We're making a statement about the universe. All the building blocks of the universe. And so this is another example where I'm warning you that scientists propose the same kinds of universal statements that were proposed to us by religion and philosophy. And yet they claim that they don't do so. They claim that scientific knowledge is based on the observation of material objects. And yet right here we have a universal statement about the whole universe, which is obviously beyond the reach of natural science. So we'll grant them this definition here, or this classification. We'll grant this classification, but we'll keep in mind that we granted this classification, that it's simply a classification that's been made up or proposed by chemists. All right? And we're going to grant it just for the sake of defining terms. A chemical element is a building material of the universe. Okay, we'll grant it. A chemical element is so simple in its structure that it cannot be broken or decomposed into a simpler substance. A chemical element is so simple in its structure that it cannot be broken or decomposed into a simpler substance. Now, we have to clarify here that this is what an element is in chemistry. This is a chemical element. When we go back to classical philosophy and we see that Aristotle identifies 4 elements in nature: fire, air, water, and earth. We have to realize that Aristotle certainly did not believe that if he read this definition, that the 4 elements that he identified would be chemical elements. Obviously, Aristotle didn't mean that fire, air, water, and earth are building materials so simple in their structure that they cannot be broken or decomposed into simpler substances. Obviously, Aristotle understood that if you dug up a bucket of soil, of earth, it contained different kinds of substances. Obviously, he could see that. So obviously, the ancient philosophers were not suggesting that there are only 4 chemical elements in the world. All right? This definition of an element, a chemical element, is a different idea with a different definition. And so we're not going to compare the four elements of Aristotelian philosophy with the chemical elements of modern chemistry. Okay? Examples of such substances would be oxygen, which you as a student, you don't know what that is, so you're taking this for granted. Okay, oxygen is a chemical element. You're taking that based on the assertion made by the textbook. All right? So you're assuming that oxygen is a building material of the universe that is so simple in its structure that it cannot be broken or decomposed into a simpler substance. And yet you have no way of knowing whether or not that's absolutely true. You're taking it based on an assumption that this textbook is true. You're also told that oxygen makes up about 1/5 of the atmosphere. And again, we're going to assume that somewhere someone actually measured that, and that observation and research is available for people to confirm. Next, nitrogen is another example. And again, you don't know what nitrogen is. You've never observed nitrogen. Nitrogen composes nearly all the remainder of pure air. You've got to, as a student, you've got to take that as a matter of faith, just as you take catechism question answers in catechism. You don't know. You don't know what nitrogen is, and you don't know that the air is composed of nitrogen and oxygen. Do you realize that in science we take these things for granted in the same way that we take religious teachings for granted? We are not making observations about material objects. We're being told what to believe, assuming that others have made observations about these material things in nature. And it may be true that they have made these observations. But do you see how the quality of this knowledge is not what it seems? You personally have no more reason to believe or know that the air is composed of oxygen and nitrogen as you do that the world was flooded in the days of Noah, and that Noah loaded all of the animals onto the ark 2 by 2, that it rained for 40 days and 40 nights, and that then the ark settled in the mountains of Ararat, and so on and so on. You have no way of knowing this as a student any more than you have any way of knowing whether the content of divine revelation or the catechism or the teachings of Aristotle or Plato are true. So you have to be careful that you don't accept this as if it's already proven and known, and just start assuming things from the very first chapters. Because this is not divine revelation. These statements are supposedly based on experiments and observations that you don't have access to. You don't know if you can trust in these statements. And so you must enter into this study, and you must commit to studying science with a critical mindset. A critical mindset that you would not take into the study of divine revelation or the teaching of the church. The church doesn't pretend that all of her teachings are based on observation. The church tells us openly right from the beginning that we believe these things to have been divinely revealed. And we teach them based on authority given to the church by Christ, and the church makes it very clear where their teaching comes from, and that it's not based on their observation. Scientists tell us that their teaching is based on observation, and yet we are given facts to believe without any proof, without any access to those observations. And therefore, we're receiving these teachings by faith in the writer of this textbook. And we need to keep that in mind, because this study isn't as innocent and simple as everyone pretends it is. Now, we can grant these statements for the sake of discussion. But when do we ever find out if they're true? When do we ever actually confirm that they're true? And even worse, how many people do you know who use what they claim to be scientific knowledge to actually reject divine revelation? When do we check to see that these things are true? That's what I'd like you to think about. Let's continue to grant the author the benefit of the doubt and assume that these things have been observed and proven, and that if we desired, we could confirm the truth of these statements by our own observation of material things in nature. Okay? Carbon is proposed as another chemical element, an element that enters into the composition of all organic living things or those that once possessed life, and over 60 other chemical elements of more or less importance to us in the study of biology. Now, it should be noted that today that number would likely be over 100. All right, so this scientific knowledge is not settled and fixed, but is apparently changing and unstable. And again, we have to be careful that we don't build our intellectual house on sand that can change and move. We have to keep scientific knowledge what it is. We have to keep it under its limits and be critical of scientific statements. Next, in the text, what the author does helpfully is provides what we could call experiments or activities that allow you to see some of these natural phenomena for yourself. So here we say it's possible to prepare oxygen. Okay, and let's just read through this little experiment that you're given. Oxygen may be easily prepared in the schoolroom or at home in the following manner. Now, what you would have to do to perform this little experiment is you'd have to purchase from a chemical supply store some basic laboratory supplies. Heat half a teaspoon of black oxide of manganese with a little more than its bulk of chlorate of potash in a test tube over a Bunsen flame or a spirit lamp, alcohol lamp. Vapors or gases will be seen to arise as the mixture becomes heated. After a moment, insert a glowing match into the mouth of the test tube, and it will burst into a bright flame. In what form does oxygen pass off from the two chemicals in the tube? How could you determine the presence of oxygen in a subject? So you're given an experiment to do. You're told to mix these two chemicals, black oxide of manganese and chlorate of potash, in a test tube, heat them, and then insert a glowing match, and there will be a bright flame. Now, I don't know how that proves to you that that's oxygen, but you're told that in doing so, that reaction between those chemicals when heated produced oxygen, which then ignited when the match was inserted. Okay? Again, I don't know how that would be considered demonstrative proof of the presence of oxygen. All right? Next, we learn about the properties of oxygen. So what we know so far is that oxygen is said to be a gas that makes up about 1/5 or 20% of the air in our environment, in our atmosphere. Here we consider a little more the properties of oxygen. The physical properties of oxygen are those which we determine with our senses. The physical properties of oxygen are those we determine with our senses. Oxygen, when carefully prepared, is found to be a colorless, odorless, and tasteless gas. In other words, we don't observe it. It has no odor, it cannot be smelled, it has no color, and therefore cannot be seen, and it has no taste, and cannot be tasted. So, the physical properties of oxygen are those which we determine with our senses. 3 of our senses know nothing of oxygen. It's not visible, it cannot be smelled, and it cannot be tasted. How then do we know it? It is known to form, so we're to accept this as known and proven by someone else. It is known to form nearly 1/2 of the Earth's surface, to form 8/9 of all water, and over 3/4 of the weight of the plants and animals inhabiting this world of ours. So, we're told that the physical properties of oxygen are those which we determine with our senses, and yet we cannot see it, smell it, or taste it. And then we jump into other properties which are not sensible. We're just told that it makes up half the Earth's surface, 8/9 of water, 3/4 of the weight of plants and animals. So we have no physical evidence that this is true. We're being taught statements that are to be accepted as things already known by others about oxygen. Fine. Now we're told oxygen has the very important chemical property of causing things placed in it to burn. If a piece of picture wire is heated red hot and then placed in a jar of oxygen, the metal will burn with a bright flame. So what properties of oxygen have we learned? So far we've learned none except that it causes things placed in it to burn. All right? There's no color, there's no odor, no taste. We were told 3 or 4 facts to simply believe as already known, and we're told that it causes things placed in it to burn. Okay? We then have a small definition of the term oxidation, or a comment about oxidation, a little experiment. Light a small piece of magnesium wire and then place it in a test tube in which you have previously made oxygen. Notice the very brilliant flame. A light-colored ash remains. This ash is magnesium oxide. In the experiment, the oxygen in the test tube unites with the magnesium so rapidly as to form a flame. This process is known as combustion. So again, we're simply told here a few points of knowledge that we're to accept as known. Oxidation and combustion. Combustion is the rapid igniting or bursting into flame of a substance, combustion. The lesson goes on to say the chemical union of oxygen with any other substance is called oxidation. So here we have a definition. The chemical union of oxygen with any other substance is called oxidation. What is oxidation? The chemical union of oxygen with any other substance, right? Can you distinguish between combustion and oxidation? So based on that little experiment with the magnesium wire being lit and placed in a test tube filled with oxygen, a bright flame takes place and an ash remains, and the ash that remains is called magnesium oxide. In other words, the magnesium has been oxidized. What is the difference between oxidation and combustion? Well, the combustion is a reaction that's produced by oxidation, right? Oxidation is a result of the combustion. Oxidation takes place wherever oxygen is present. These facts, as we shall see later, have a far-reaching significance in the understanding of some of the important problems of biology. So as we go, we'll continue to grant this author the statements that he makes under the assumption that these things are in fact known by others through observation of material things. But we have to keep in mind, again, that there's going to need to be a time when we confirm these things. Otherwise, our entire knowledge of biology is based on faith and not on scientific knowledge. Not on scientific knowledge that we possess. For us, it's merely faith. Someone else may know it by observation. But so far for us, in this study, in this chapter so far, this is a doctrine that we're being asked to accept by faith. So let's be conscious of that. We're learning about oxygen. We're learning about the properties of oxygen. We've learned about, really all we know so far about oxygen is that it causes things placed in it to burn. And we learned about this concept of oxidation, the combining, the chemical union of oxygen with some other substance. We're told that this takes place whenever oxygen is present and that it's very important in understanding problems of biology. Then he speaks of oxidation of a match. The simple process of striking a sulfur match, a common match. The red chemical on the tip of a match is said to be sulfur. The simple process of striking a sulfur match gives us another illustration of the process of oxidation. The head of the match is formed of a composition of phosphorus, sulfur, and some other materials. Phosphorus is a chemical element distinguished by its extreme inflammability. In other words, it doesn't burn. Phosphorus. It unites with oxygen at a comparatively low temperature. Sulfur is another chemical element that combines somewhat easily with oxygen, but at a much higher temperature. The rest of the match head is made up of red lead, niter, or some other substance that will release oxygen, and some glue or gum to bind the materials together. The heat caused by the friction of rubbing the match head against the striking surface is enough to cause the phosphorus to ignite. So by inflammability, we have to assume that what's actually meant there was flammability. Okay? Striking the surface is enough to cause the phosphorus to ignite. This in turn ignites the sulfur and finally the wood of the match, composed largely of the element carbon. That is lighted and oxidized. If we could take out the different chemical elements of which the match is formed and oxidize them separately, we should find that the amount of heat needed to start the oxidation of the substances would vary greatly. The element phosphorus, for example, is kept under water in a glass jar because of the extreme readiness with which it unites with oxygen. Okay, so some simple observations we're told about how matches produce flame and why they're made the way they are. Let's move on with our study of oxidation. One of the most important effects of oxidation lies in the fact that when anything is oxidized, heat is produced. This heat may be of the greatest use. Coal, when oxidized, gives off heat. This heat boils the water in the tubes of a boiler, steam is generated, and the wheels of a steam engine turn, and work is performed. So the oxidation or burning of coal is used to produce steam, which is used to power a steam engine. The energy released by the burning of coal may be transformed into any kind of work power. Energy, here we have another definition. Energy is the ability to perform work. Energy is the ability to perform work. So that's what we learn about oxygen. Basically, oxygen is a chemical element in which things are able to burn. That's what we've learned about it. And that things combine with oxygen through a process called oxidation, and that heat is given off by oxidation, and that heat can be used to do work, and the ability to perform work is called energy. So oxidation gives off energy in the form of heat. Next, we learn about the chemical element carbon. Another chemical element of much importance to us is carbon. This element makes up an important part of all things that now have or at any time had life. In other words, organic substances. Such matter we call organic. Carbon is found making up part of the bodies of plants and animals, of coal, and in a nearly pure state in a diamond. The presence of carbon can often be detected by the fact that the substance containing carbon turns black when heated in a flame. And so our textbook is telling us that when we burn something, the black substance that's produced is carbon. All right. Moving on. Nitrogen, the third chemical element we're learning about in this chapter. There is another gaseous substance. And what it means by gaseous would mean that at normal temperatures it's a gas. There is another gaseous substance that will not support combustion. This is the element nitrogen. Its presence in the atmosphere can be shown by the following experiment. So supposedly this experiment shows us that this chemical element, nitrogen, is present in the atmosphere. Invert a bell jar in a large deep dish of water, having previously placed within the jar on the surface of the water a piece of phosphorus supported on a flat bit of wood or cork. Leave the experiment for at least 2 days undisturbed. After that time, the water will be found to have risen considerably in the jar. If you make a mark on the cover to show where the water stood, you may measure the space occupied by the water in the jar. The space will be found to be almost exactly 1/5 of the cubic contents of the jar. It was occupied by the oxygen of the air, this having been used up by the oxidation of the phosphorus. The remaining space at the completion of the experiment is occupied by the nitrogen, which makes the remaining 4/5 of the atmosphere. So this experiment starts with the assumption that oxygen makes up 1/5 of the air in our atmosphere and nitrogen makes up 4/5 of the air. Since phosphorus oxidizes by joining itself with oxygen, the oxygen would be consumed, and what would be left, again, based on the assumption that the air contains nitrogen and 4/5 nitrogen, would be nitrogen. Okay? So that experiment, scientifically or absolutely speaking, proves to us that there's something in the air other than oxygen, maybe. But it doesn't necessarily prove that that substance is nitrogen. But anyway, you see the point of a clever experiment. All right? The physical properties of nitrogen, physical properties, these are properties that we can observe with our senses, as was defined earlier. It lacks color, taste, and odor. So again, the physical properties are that there are no sensible properties. There's no color, no taste, and no odor. We cannot see nitrogen, we cannot taste nitrogen, we cannot smell nitrogen. So that's interesting to call those physical properties when they actually are not property, are not sensible. Okay? Its chemical characteristics are its inability to support combustion and its slight affinity to for other substances. Okay, so just like with oxygen, we're actually told there are no physical properties that we can sense, but there is a chief chemical characteristic in that it does not allow objects to burn as oxygen does. All right. Then there's a section on mineral matter in living things. We saw in the experiment for the detection of carbon by burning that the sand or gravel contained no carbon. If a piece of wood is burned in a very hot fire, the carbon in it will all be consumed, and eventually nothing will be left except a grayish ash. This ash is what is seen after a wood fire in the fireplace or after a bonfire of dry leaves. This ash consists entirely of mineral matter, which the plant has taken up from the soil, dissolved in water, and which has been stored in the wood or leaves of the plant. So the organic matter burns away. What's left behind is an inorganic matter that's called mineral matter. If we were able by careful analysis to reduce a plant and an animal to the chemical compounds of which they are formed, we should discover that both contained mineral or inorganic material. Notice he says we're not able to do this analysis. If we were able, by careful analysis, then we should discover, that's again another strange thing to say in a scientific textbook, to say if we were able to perform this operation, then this would be our result. Now that's not scientific observation. That's a conclusion that's proposed and assumed would take place if an experiment was conducted. Again, it's just a strange idea in a science textbook. We have just seen an example of this in plants. Mineral matter is found in bone, in the shells covering mollusks, and in many other parts of the bodies of animals. So inorganic material is taken up into living things, and when they die and decay or are burned, that inorganic matter remains behind and returns to the earth. Okay? So there is mineral matter or inorganic material in living things, supposedly, and water in living things. Next, water forms an important part of the substance of plants and animals. Remember, water is one of the 4 classical elements of nature. Water forms an important part of the substance of plants and animals. This can easily be proved by weighing a number of green leaves placing them in a hot oven for a few moments, and then reweighing the leaves. How much weight of a given quantity of leaves is made up of water? Make the same experiment with soft-bodied animals such as an oyster removed from its shell. Some jellyfish are composed of almost 99% water. The human body contains 60% water. So it's proposed that to prove that leaves, for example, concern a great deal of water, if we take some moist, fresh leaves and put them in an oven and bake them, that the heat of the oven will cause the water to be absorbed or to evaporate out of the leaves, and the weight of the leaves that's left behind will be the weight of the organic matter of the leaves minus the weight of the water. Next, gases present. Some gases are found in a free state in the bodies of plants or animals. Oxygen is, of course, present wherever oxidation is taking place. So this is an interesting logical argument. We say that oxygen causes oxidation, and then we say that if we see oxidation taking place, that's proof that there's oxygen. But that's a circular argument. Okay? To say oxidation proves oxygen assumes that oxygen causes what we call oxidation. In all of this, we're assuming that somewhere, somehow, scientists observed and proved the truth of these conclusions. We can grant these assumptions, but we as students have no proof for any of this so far. Next, the classification of organic matter. The organic or living part of a plant or animal is made up largely of the elements carbon, hydrogen, oxygen, and nitrogen. Okay? The organic or living part of a plant or animal is made up largely of the elements carbon, hydrogen, oxygen, nitrogen, and a very minute amount of several other elements which collectively we may call mineral matters, which we just learned about. Okay? That's being presented to you to be accepted by faith. Right? That organic, the bodies of plants and animals are made up chiefly of carbon, hydrogen, oxygen, nitrogen, and a small amount of mineral matter. If we were to separate a plant or animal chemically into various organic compounds, we should find it composed of various groups of tissues, the chemical compositions of which are more or less alike. If we were to actually do that. For example, the living part of a plant corresponds chemically with the living part of an animal. In other words, the chemical composition of animals and plants, the parts of animals and plants, are said to be similar. The starch found in grains or roots of plants has nearly the same chemical formula as the animal starch found in the liver of man. That's presented to us as a known fact to be believed. The oils of a nut or fruit are of composition closely allied to the fat in the body or in a sheep or cow. The fats in plants are similar to the fats in animals. Again, that's presented to us to be believed. These building materials of a plant or animal may be placed in one of the three groups of organic substances: carbohydrates, materials containing a certain proportion of carbon, hydrogen, and oxygen are called carbohydrates. Organic fats and oils, which contain chiefly hydrogen and carbon, and nitrogenous or proteid or protein substances, which contain nitrogen in addition to the above-mentioned elements. So carbohydrates are said to contain carbon, hydrogen, and oxygen. Organic fats, which contain chiefly hydrogen and carbon, rather than oxygen, and nitrogenous or protein substances which contain nitrogen in addition to the other elements. The above three kinds of organic materials form the organic foods of all animals and plants. Now we go on to a brief study of food. What is a food? We know that if we eat a certain amount of proper foods at regular times, we shall go on doing a certain amount of work, both manual and mental. We know too that day by day, if our general health is good, we are adding weight to our body, and that added weight comes as the result of taking food into the body. What is true of a boy or girl is equally true of plants. If food is supplied in proper quantity and proportion, they, plants, will live and grow. If the food supply is cut off or even greatly reduced, they will suffer and may die. From this, the definition which follows is evident. So this is a definition of food based on simple observation of how animals and plants respond to food or a lack of food. A food is a substance that forms the material for the growth or repair of the body of a plant or animal, or that furnishes energy for it. So there we have a definition of food. The next section treats of nutrients. Food substances, so food refers to a general group of substances which provide the body with energy for growth and repair. Bodies of plants or animals. Food substances may be classed into a number of groups, each of which may be detected by means of its chemical composition. Such food substances are known as nutrients. So nutrients are the chemical substances that make up foods, nutrients. Let us now examine a few of the nutrients that we're likely to meet with in our daily life and see how we could test chemically for their presence. So first we learned about carbohydrates. Those are substances we're told are composed of carbon, hydrogen, oxygen, and nitrogen. Starch and sugar are common examples of this group of substances. All right, so starches and sugars are examples of carbohydrates, and there's a little example to test for starch. Grape sugar or fruit sugar. There are several forms of sugar commonly used as food. For example, cane sugar, which is the white sugar most of us use in the house. Beet sugar, which is not common today, but was often used on farms where you could grow beets and use the beets to produce a sugar or sweetener. And then grape sugar, which is known as glucose. Glucose or grape sugar is manufactured commercially. So they produce sugar in great quantities by pouring sulfuric acid over starch. This is used as an adulterant for many kinds of foods, especially syrups, honey, and candy. Okay, so at that point in time, at the time this textbook was written, this glucose was produced by pouring sulfuric acid over starch to leave behind or produce this grape sugar or glucose. In modern foods, you'll see corn syrup is usually the most common source of a sweetener. Corn syrup is produced from corn, which is grown in incredible quantities in America. Not from sweet corn, which we eat as a vegetable, but from another kind of corn that's used to feed animals. It's sort of a harder, dry corn. It's called dent corn. That corn is used to produce corn syrup. So our textbook here talks about grape sugar or glucose. Today might be comparable to what we would call corn syrup. Next, protein. So that's an example of a carbohydrate. Proteins, nitrogenous foods, foods containing nitrogen. In addition to carbon, hydrogen, and oxygen of the carbohydrates and hydrocarbons, nitrogenous foods or proteins contain the element nitrogen in addition to carbon, hydrogen, and oxygen of the carbohydrates and hydrocarbons. Hydrocarbons refers to fats. They include some of the most complex substances known to the chemist, and as we shall see, have a chemical composition very near to that of living matter. Proteins occur in several different forms, but the following tests will cover most cases commonly met. White of eggs, egg whites, lean meat, beans, and peas are examples of substances composed in a large part of proteins. So egg whites, lean meat, and the reason they don't just say meat is because a large proportion of meat is normally fat. Beans contain protein or contain nitrogen, and peas. These are examples of proteins. And that brings us to the end of this chapter. Now, what you see is I've walked through this chapter critically. Okay? I'm not saying that these statements made in the textbook are false. I'm not saying that they're false, but I'm saying many things are being presented to us that we ourselves are unable to confirm or prove, that we're receiving by a kind of faith in the truthfulness of our textbook. And I want you to see that, because in chapter 1 or in lesson 1, we went from saying that scientific knowledge was knowledge that's gained through observation of material things, and that sounds so great. What can go wrong if we're simply observing material things around us? That's great. Then we move into chapter 1, and we've been presented with a large number of statements that are said to be scientific, and yet we have none of the proofs of this information. How do we know that the air contains oxygen and nitrogen? How do we know that? It's colorless, odorless, and tasteless. Why can't we just call it air? Why would we assent to the statement that the air contains oxygen and nitrogen when we have no means of proving that? Okay? So we can grant these statements and assume them to be true. But what we're building in ourselves is not really a scientific knowledge. The scientific knowledge may be present in a scientist who conducted the research, carried out the experiment, observed the results, and so on. He may possess a scientific knowledge, but we don't possess a scientific knowledge. We're simply accepting things by faith. And that's not scientific knowledge. Okay, so this is the dilemma in modern science. And again, I'm not saying that any of the content of this lesson is false. But what I'm saying is that everything in it requires us to accept it by a kind of faith. And so scientific knowledge is not being produced in us. All that's being produced in us is a kind of faith. The scientific knowledge can only be possessed by the actual observer of these material things in nature. And we're not building that kind of knowledge in this study. We're building a kind of faith. Now, again, I'm not saying that these statements are false. I'm just saying that they are not of a scientific quality. It's helpful for us to learn these things, and what I'm going to advise you to do, for the sake of the study of biology, is to think that what we're going to do is study to learn the content of modern biology. We're going to study to learn the content of this textbook, of modern biology. But what we are not going to do is granted the certainty of scientific knowledge. We're going to admit that this, thus far, is a matter of faith received by a student. Okay? And yet we're going to study to learn the content of biology so that we can prove that we understand and know what biology teaches. Okay? But be careful to keep separate the knowledge of what biology teaches and the actual confidence in that knowledge, as if you possess a scientific knowledge which you do not possess. Okay? That's a long video, an hour I see. I hope that's a helpful introduction to this chapter. Again, this problem in modern science is a very serious problem, and I want to show you how common it is in modern science studies. And remember this, keep separate the knowledge of what biology teaches and your actual knowledge of the natural world. Your scientific knowledge does not consist of all that biology teaches, because much of it is unknown to you scientifically, and you have no proof for it. I hope that's helpful. Study the chapter on your own for mastery and submit the lesson assignment, and we'll continue our study of modern biology. God bless your studies.